Hi everyone. Today I will be discussing big data and genomics. The first question you may have is, what is genomics? Genomics is a study of the complete genetic material of organisms. This includes sequencing, mapping, and analyzing a wide range of DNA and RNA codes. You can imagine the massive amounts of data produced by this process. The reason why millions of dollars are being put into studying genomics is because we want to be able to better understand the genetic basis of our heritable traits. By doing this, we can prevent and cure diseases. We will also be able to tailor medicine specifically towards individuals rather than live by a one-treatment-fits-all system. As I mentioned earlier, the amount of data being produced by sequencing, mapping, and analyzing human genomes is massive. To put it into perspective, each human genome has 20 to 25,000 genes comprised of 3 million base pairs. That's 100 gigabytes of data. In other words, 102,400 photos. By sequencing multiple genomes, all this data would quickly add up to hundreds of petabytes, 1 petabyte being 10 to the 12th bytes. And with the advancement of technology, we can expect in the next 5 years that we'll be able to function at the exabyte level, which is 10 to the 18th bytes of data. The first effort in analyzing all this data was initiated in 1984 with the Human Genome Project. By the time it was declared completed, the cost of sequencing a human genome had decreased from $95 to $40 million. Scientists are trying to make this process as cheap as possible to make it available for public use one day. Now, one human genome can be sequenced for $5,000. However, the ultimate goal is to lower the cost down to $1,000. The Archon X Prize $1,000 Genome Prize competition has been an incentive for scientists to accomplish this. There already exists sequencing centers for analyzing and storing data, but the real challenge here is combining these datasets across different archives and cross-referencing them with patient records, treatments, and outcomes. For this, we have two primary methods of processing this much data: cloud-based computing and the Apache Hadoop project. Let's first take a look at the cloud-based computing. Cloud-based computing is the only storage model that can provide the elastic scale needed for DNA sequencing. It functions on a pay-per-use model for enabling convenient, collaborative, and on-demand network access to a shared pool of configurable computing resources that can be quickly provisioned and released with minimal management effort. Below is a list of positive characteristics of cloud-based computing. Take note of virtualization. In this diagram, it shows the difference between a traditional model to one that utilizes virtualization. With traditional computing, applications interact with the hardware via one instance of the operating system. With visualization, multiple OS images share the hardware resources, which are allocated and managed by virtualization software known as a hypervisor or the virtual machine monitor. This ensures maximum utilization of hardware and capital investment. A virtual machine, VM, is a software application that emulates a physical computing environment with an operating system. Associated applications can run with multiple VMs installed on a single machine. Cloud-based computing can be categorized into three subcategories: infrastructure as a service, platform as a service, and software as a service. Each differs in level of functionality provided to the user by the cloud provider. Choosing which one to use is decided based on the user's requirements. This diagram shows visually the limited or unlimited nature of each model. The areas circled in red show what is not controllable by the users, while the areas shown in green show what is. As you can see, the IaaS model provides the most freedom to the user, while the SaaS model provides the least. Apache Hadoop is an open-source software framework for storage and large-scale processing of datasets across clusters of computers using simple programming models. It's designed to scale up from single servers to thousands of machines with a very high degree of fault tolerance. Rather than relying on high-end hardware, the resiliency of these clusters comes from the software's ability to detect and handle failures at the application layer. Apache Hadoop has two main subprojects: MapReduce, which has the ability to take a query over a dataset, divide it, and run it in a parallel over multiple nodes, and HDFS, which is a file system that spans all the nodes in a Hadoop cluster for data storage. It links together the file systems on many local nodes to make them into one big file system. HDFS assumes nodes will fail, so it becomes reliable by replicating data across multiple nodes. The benefits of Hadoop include its scalability, in that new nodes can be added as needed with ease, and its cost effectiveness, in that Hadoop brings massively parallel computing to commodity servers. It's flexible because it can absorb any type of data and is fault tolerant. When you lose a node, the system redirects work to another location of the data and continues processing without missing a beat. The benefits of applying big data methods to genomics are limitless. First, it presents the possibility of eliminating cancer. Cancer mutates differently for every individual and reacts in unexpected ways with people's genetic makeup, but with big data processing methods, individualizing medicines is becoming a reality. Also, we can detect diseases at an earlier stage when they can be treated more easily and effectively. Not only that, but we can predict or estimate outcomes like length of stay of the disease, patients who wouldn't benefit from a surgery, complications, and much more. It has been estimated that big data analytics can enable more than $300 billion in savings per year in U.S. healthcare. This project has a wide support base, with startup companies appearing to dedicate their missions to making genomic data usable information that can improve the health of the general public. These organizations portray the evolving state of the art in using genomics to help personalize medicine, each with their own specific methods of processing data. That's all for today. Thank you for your time.